Hello and welcome everybody back to lecture video 7.2. In the previous video we've introduced how we can estimate the 2D motion in camera images, and now in this video we will extend this to allow a quadrotor to estimate its horizontal speed using visual odometry. So as you remember from our lecture on control, there are actually several control layers stacked in a quadrotor. So at the lowest level we have this motor speed estimation and a motor speed controller. Then we have an attitude estimation, typically using the IMU, the gyroscopes. And then we have an attitude control that, for example, uses a PID controller. And then on top of that we have typically a visual or a localization module that can be based on a camera, for example, and that is then used to support velocity and position control for the higher levels of trajectory control, for example, but also to simplify life for a human pilot. And today we will look at this visual localization block over there. Today we will only look at the so-called visual odometry problem, but we will then extend this next week to full visual SLAM. So the basic problem here is that the velocity estimates that we're getting from our IMU are generally very inaccurate, at least for small UAVs like quadrotors that we're looking at. The problem is that the IMU, as you know, consists of gyroscopes and accelerometers, and in particular the accelerometers estimate accelerations, and if you integrate accelerations you end up with velocities, and if you integrate twice then you end up with positions, but any error or any noise that you have in your accelerations will end up as strong errors in your velocity, in integrated velocity, and even larger errors in your position. And this means that typically you can only use the IMU to propagate or to estimate your velocity and position for maybe half a second or a few hundred milliseconds. So the question is, how can we get more accurate velocity estimates that are less sensitive to this noise from the IMU? And the constraint, of course, is that we need to have these estimates in real time, because we need them in our control loop immediately, and we want to have minimal delay because we need it in control. And the basic idea is now that we have a quadrotor, and the quadrotor has a downward-looking camera. And from this camera image, it tries to track one or more points in the camera image, and then from this motion in the image, it tries to compute back the motion of the quadrotor in the 3D world. So one first observation here is that that if we only would use a single monocular camera, then we could not determine the absolute speed. And the reason for that is that with just one eye you can't really tell how far the world is away or how large the world is. So the same motion in the 2D image could correspond to different distances in the real world depending on your flying height. And this actually means that we need additional sensors, and very the common choice then is to use first of all the IMU, because we have that anyway. This gives us the absolute orientation of our quadrotor. Typically there is also a height sensor being used that gives us the absolute scale then of the world. For that you can use, for example, ultrasound, as it is used on a Faraday Ardrone, or you can use a pressure sensor that also so change in pressure also corresponds to change in height. One strong assumption that is typically made with these visual odometry sensors that we will look at in this video is that we assume a planar floor. This is strictly speaking not necessary. We will later see how we can relax this assumption, but for the moment we assume that we are looking at a perfectly planar floor. Good. So here are again our assumptions. We look at, for the moment we assume that we have a camera that's perpendicularly looking onto a planar ground. And furthermore, we assume that we know our flying height, for example, from an ultrasound sensor or from somewhere else. And then we have a camera image, and we look at a particular point, say here, for example, this point exactly in the center of the image, and we try to drag it as the quadrotor moves. So, for example, in the next image, the quadrotor has moved a little bit now to the right. It still keeps tracking this point that was previously located in the center of the image. Now it is shifted slightly to the left with respect to the new camera coordinate. And this point in the world is now imaged onto the image plane. So we can, and this is what we get out of the 2D motion estimation on the image. So we make an observation in the image that this point has shifted by a certain number of pixels u and v. And of course, there is now a relationship between this point in 2D and the point in the real world in 3D, and that is given by this equation here in the middle, where we say that x tilde equals k, where k is the intrinsic matrix of our camera, times our 3D point. And this 3D to 2D perspective projection, of course, goes now in the wrong direction because we want to know the point P, but we know x tilde. Remember that this tilde means that that this entity is a homogeneous vector, so it contains our image coordinates u and v, but it might be scaled arbitrarily by a factor lambda. And this homogeneous coordinate now equals the product of the intrinsic matrix times our 3D point. And if you look carefully at that, then you see that if you only look at the last column, it says that lambda equals z. So we can identify lambda here with z now, and then solve for p. So we can just do that by multiplying with k-1 on both sides of the equation, and then we end up with this very simple expression. And we can directly now read off the motion in x and y direction in world coordinates. Of course, the quadrotor is not as friendly and always look downward looking perpendicular to the floor, but of course the quadrotor tilts a lot during flight. So this means that the second image might be tilted slightly, but we still assume that it's tracking this point that we've been looking at in the first frame. And now, because we have this IMU on board, we actually know the amount of rotation, the relative rotation between these two camera frames, and this actually allows us to derotate this camera to create a virtual camera that is located at the same spot in the world, but it is looking perpendicular to the floor again. And there is a very easy relationship now between the point that the tilted camera observed and the point that would appear in this derotated virtual camera. So because if we know this rotation r from our IMU, we can just multiply this rotation by this observed point p, or this point p in the tilted camera frame, and this gives us a point p prime. That is now expressed in this perpendicular camera. And this means now that for this virtual camera, we again have the situation from the last slide where we just had a pure translation, and now we can fill in that in our equation as before. So we're now getting the x and y motion by derotating it using this r to the -1. You know, this is actually exactly the same as r transposed times the inverse of the intrinsic matrix times z times this homogeneous vector uv1. So of course the quadrotor not only flies in one plane, but it also changes its flying height. And then let's look at what this actually means. So if the quadrotor is now changing its height, but still keeping track of the same point, then this point appears at different locations in the image plane. The further the quadrotor is, the higher the quadrotor flies, the smaller the world appears, and so the smaller this shift in the image plane becomes. So we see from this sketch here that the pixel coordinate actually gets scaled by the ratio of the two flying heights. So now we not only need the flying height from the first camera, but we also need to know the flying height of the second camera. But if we know that, then we can again create a virtual observation x prime, where we scale the two pixel observations u and v by this factor. And then again we can plug that into our previous equation that we had, and this now gives us the full formula how to come from pixel observations of 2D motion estimate in the image plane to 2D velocities in the real world. Good. So far we only tracked a single point now for illustration, but of course it's clear that if you only look at a single point, then you're quite sensitive to noise and outliers. Of course, this can be the accuracy and the robustness can be increased greatly if you not only track a single point, but a whole bunch of them. For example, the Pix4Flow sensor that we will look at in a second actually tracks an array of 4x4 points in the image, and then it runs a majority vote algorithm, sample consensus methods like RANSAC, to find the motion hypothesis that has the largest support from all of the points. Now, two hardware implementation examples. All of you know the Parrot Ardrone, of course, and the main board and navigation board together form such a visual odometry sensor. There is a downward-looking camera. There is an IMU, an ultrasound sensor to determine the absolute flying height, and a pressure sensor that the Ardrone can use when it ascends higher than 5 meters, because ultrasound only works up to a certain height, of course, because at some point you don't hear your echo anymore. Yeah, so this is only needed for larger flying heights if you're going outdoors in particular. Pressure indoors is always difficult because as soon as somebody opens a window or a door, then your pressure changes, and so it's not really informative. An alternative to the Parrot board so one disadvantage of the Parrot board is that it's closed source, so we don't really know what's going on in there. There is actually a research paper that you can read, but it doesn't go too much into the details, and there is no code available. In contrast, people from ETH, from Mark Polyphase Group, actually developed this Pix4Flow sensor and released it as open source and open hardware. So you can buy it pre-assembled, but you can also look at the software then, and of that we know much better how it works and what its properties are. So to look at that in a little bit more detail, it's a so-called smart camera module because it combines a camera with a processor. This camera can run at reasonable resolution, but of course for our application it's desirable that it runs at a really high frame rate. This one can run at 250 frames per second, and then you still get a reasonably high resolution image. It also has a zoom lens on it, which means that the opening angle actually is quite narrow. This has the advantage that we're then looking at, so we made this assumption that the floor is planar, and of course if you have a wide angle camera then you see all kinds of things, including the walls and maybe objects and persons walking around. So it's an advantage to have a zoom lens, because then you're focusing on a small patch of the world, and then the likelihood that this patch actually is planar is much larger. Yeah, good. And then there is also a full processor that runs at 168 megahertz, so this is quite something. It even can do single precision floating point operations, and as I said, the software running on this processor is actually open source, so you can download it, have a look at it, even potentially modify it or replace it by completely your own implementation. Furthermore, there is a gyroscope on board that we need to estimate the rotation change. There is also accelerometer integrated. And there is an ultrasound sensor. As you can see here, this is actually the sender and receiver in one module. So the Parrot Ardrone had a separate sender and receiver, and this module here has both integrated in the same thing. And then the sensor does everything we need, so it directly outputs the computed X and Y speed over a serial link. It also outputs, by the way, the gyroscope information, so you can use that as well then in the Kalman filter and use that for position control. So this is now a demo that shows how this looks like. This is a modified Parrot Ardrone, but it's just the hardware left and the motor controllers. Everything else got replaced. by the authors. Now this visual odometry sensor is running there. It's looking downwards. Here Dominic Honegger shows the remote control, that he's not touching any controls, and still the quadrotor is keeping its position. And now the cool thing is that you can directly control speeds, absolute speeds in the world coordinate frame. So he can command that the Ardrone goes up and down, and he can command that the Ardrone goes forward and backward, left and right. And for that it's just using this visual odometry sensor with this downward-looking camera. And the cool thing, of course, is if you have visual odometry, then it greatly simplifies the navigation task for the pilot, because you don't need to worry about compensating for disturbances. The quadrotor will stay in place wherever you leave it, and so on and so on. Good. Here is another video that demos that you can see the Ardrone is rock solid, standing in the air. It doesn't need any special markers on the floor. A little bit of texture is enough, but most floors actually have that. And and you can also see here the whole electronics that got added to the Ardrone. It's not only this optical flow sensor, but it's also a different autopilot. This is now another another quadrotor. You can also see that the same works there, and this is now you can see that it also works outdoors. Good. They also ran some evaluation here. This is to see how well so visual odometry by itself is still prone to drift, but it drifts much less than the IMU. But nevertheless, it's of course interesting to evaluate how large this drift is, and to illustrate that there is actually quite little drift, they ran the following experiment. They went outdoors and walked along through the university park at ETH at a relatively low flying height, manual control, and then they were manually flying this quadrotor that was carrying this Pix4Flow sensor, and they were just integrating up the position estimates from the sensor. It's important to note here that there was no GPS involved, so the trajectory they got out of that, they overlaid this to this aerial image from Google Maps, and then you can see that the trajectory matches nicely the footpath on the campus, and this is a good indication that actually the sensor provides reasonable visual odometry. I should mention that there are also alternative methods to compute visual odometry with different sensor setups. For example, there is the possibility to use a stereo camera or a depth sensor like Kinect. We will look at the direct visual odometry method for that next week. But there is also the possibility to use a wide-angle lens and an IMU, and not to use any ultrasound sensor, but to use the IMU directly to estimate the scale. So, and this is, for example, was implemented by Stefan Weiss from Roland Siegwart's group at ETH. The idea there is to use PTAM, which is a monocular visual SLAM library from Klein and Murray, developed presented at ICRA 2007. It builds a sparse 3D map from visual features. So it runs something similar to this KLT tracker that you've seen before, but then it additionally estimates the 3D position of every feature in the world, and then it uses that again to compute the camera pose, or to track the camera pose in the world. The problem with the visual SLAM system in general is that it gets slower and slower the more keyframes you add. And so the idea of Stefan Weiss was to drop old keyframes, to just have a limited or a fixed number of keyframes within your buffer to keep the computation time actually constant. And with that, you can guarantee that you can compute the visual odometry at a reasonable frame rate of 30 Hertz around that. And then, as I said, they also used the IMU then to estimate the scale. This is also viable and possible. It's a bit more noisy than if you directly get your height estimates, of course, from an ultrasound sensor, but it's nevertheless possible, and you need less hardware. So this video here demos that principle now. This is was recorded in the mocap area from Raffaello D'Andrea at ETH. You can see here that the quadrotor is flying a small rectangle, and it's using its this visual odometry method here and spits out its position estimates here on the right. You can see that sometimes there is a little bit of noise, especially when the quadrotor shakes a lot. But nevertheless, you can recognize this this rectangle that it flew, and in this way you can do position control and stabilize your flight. So to summarize the video of today, we've looked at visual odometry methods for UAVs. We've introduced one particular sensor setup that's used quite frequently in more detail and introduced the basic algorithm. And we've also briefly looked at alternative methods for computing visual odometry that are also used a lot on quadrotors. Next week is our last week actually, and there we will in particular present the cutting edge research results from our group. So we will show some some very exciting research work that we've done over the past years. As far as possible, I'll also point you to additional references then in case that you want to extend upon this work.